Welcome to a fascinating exploration of the invisible yet omnipresent phenomenon that surrounds us, sound. Sound is not just a simple noise. It's a complex interplay of vibrations and waves that travel through various mediums, shaping our perception of the world. Today, we'll unravel the mysteries of sound, delving into its nature, how it propagates through air, and the myriad ways it influences our lives. So, let's embark on this sonic journey and discover the physics behind the sounds that fill our universe. Sound is a type of energy made by vibrations and travels through a medium such as air, water, or solid. When an object vibrates, it causes the particles in the surrounding medium to vibrate as well, creating a chain reaction that propagates through the medium as a sound wave. This wave carries energy from the source of the vibration to the listener's ear, where it is perceived as sound. Sound waves are longitudinal waves, meaning they travel in a direction parallel to the direction of vibration. These waves consist of compressions, areas where particles are closer together, and rarefactions, areas where particles are further apart. As the wave moves through the medium, particles move back and forth in the direction of wave propagation, transferring energy without moving from their initial positions. Sound waves have several key properties: wavelength, frequency, amplitude, and speed. The wavelength is the distance between two consecutive compressions or rarefactions, determining the size of the wave pattern. Frequency, measured in Hz/Hz, is the number of wavelengths that pass a given point per second and determines the pitch of the sound, with higher frequencies corresponding to higher pitches. Amplitude is the maximum displacement of particles from their resting position and is related to the loudness of the sound, with greater amplitudes resulting in louder sounds. The speed of sound is the rate at which the sound wave travels through the medium and can vary depending on the medium's properties, such as density and temperature. Sound waves are generated by vibrating objects. For example, when a guitar string is plucked, it vibrates and causes the air particles around it to vibrate as well, creating a sound wave. Similarly, a speaker diaphragm vibrates when an electrical signal is applied to it, producing sound waves. In both cases, the vibrating object transfers energy to the surrounding medium, initiating the sound wave. Sound waves travel through air as a series of compressions and rarefactions. As the wave passes through, air particles move back and forth, transferring energy to adjacent particles. This process continues, allowing the sound wave to propagate through the air. The movement of particles is what enables sound to travel from one location to another. The speed of sound in air is approximately 343 meters per second at room temperature, 20 degrees Celsius, and can be affected by factors such as temperature, humidity, and pressure. For instance, sound travels faster in warmer air and slower in cooler air. Humidity also plays a role, as moist air is less dense than dry air, allowing sound to travel slightly faster. Additionally, air pressure can influence the speed of sound, although this effect is generally less significant than temperature. Our ears capture sound waves and translate them into signals that the brain interprets as sound. The outer ear funnels sound waves into the ear canal, where they vibrate the eardrum. These vibrations are then transmitted through the middle ear to the inner ear, where they're converted into electrical signals that the brain processes as sound. The intricate structure of the ear allows us to detect a wide range of frequencies and amplitudes, enabling us to perceive differences in pitch, loudness, and timbre. Pitch is determined by the frequency of the sound wave, with higher frequencies perceived as higher pitches. Our ears are sensitive to a range of frequencies, typically from 20 Hz to 20 kHz. Loudness is affected by the amplitude of the sound wave, with greater amplitudes perceived as louder sounds. Loudness is also influenced by the sensitivity of the ear to different frequencies. Timbre is the quality or character of the sound, influenced by the waveform and determined by the object's material and shape. Timbre allows us to distinguish between different musical instruments or voices even when they are playing the same note at the same loudness. Sound waves exhibit various behaviors such as reflection, refraction, diffraction, interference, and resonance. Reflection occurs when sound waves bounce off surfaces, similar to light waves, and is why we can hear echoes. The angle at which a sound wave is reflected depends on the angle of incidence and the properties of the reflecting surface. Refraction happens when sound waves bend when they pass from one medium to another with a different speed of sound, such as when sound travels from air into water or from warm air into cooler air. Diffraction allows sound waves to bend around obstacles or pass through openings, enabling us to hear sounds from sources that are not in direct line of sight. The amount of diffraction depends on the size of the obstacle or opening relative to the wavelength of the sound. Interference occurs when two sound waves meet and can either reinforce each other, constructive interference, or cancel each other out, destructive interference. This phenomenon is used in noise-canceling headphones to reduce unwanted sounds. Resonance is a phenomenon where an object vibrates at its natural frequency when exposed to sound waves of the same frequency, often leading to amplification of the sound. Musical instruments rely on resonance to produce sound, and it is also a critical concept in the design of acoustic spaces. The physics of sound is crucial in the design of various technologies. Headphones and speakers utilize the principles of sound wave generation and propagation to deliver audio. High-quality headphones and speakers are designed to minimize distortion and maximize fidelity, providing an accurate representation of the sound source. Soundproofing materials are designed to absorb or block sound waves, reducing noise pollution, and are essential in creating quiet environments in homes, offices, and industrial settings. In scientific and medical applications, ultrasound is used in medical imaging to visualize internal body structures and also has therapeutic applications, such as breaking up kidney stones. Ultrasound technology relies on the reflection and transmission of high-frequency sound waves through the body. Simple experiments can help us visualize and understand the properties and behaviors of sound waves. For example, the tuning fork experiment involves striking a tuning fork and placing it near a suspended string or a surface of water to visualize the vibrations. The vibrating tuning fork will cause the string or water to oscillate, demonstrating the transmission of sound waves. Another experiment involves using a long tube to demonstrate how sound waves travel and how changing the length of the tube affects the sound, illustrating the concepts of resonance and standing waves. In conclusion, sound is a fascinating form of energy that travels through mediums as waves, composed of compressions and rarefactions. Its properties, such as wavelength, frequency, amplitude, and speed, determine how we perceive sound in terms of pitch, loudness, and timbre. Sound waves exhibit various behaviors like reflection, refraction, diffraction, interference, and resonance, which are crucial in both technological and medical applications. Simple experiments can help us visualize and understand these properties and behaviors. The physics of sound is a rich and complex field with endless possibilities for exploration. Whether you're intrigued by the mechanics of sound propagation, the perception of sound, or its applications in technology and medicine, there's always more to discover. So, let your curiosity be your guide. And who knows? You might just uncover the next breakthrough in acoustics. Thank you for joining us on this sonic voyage. The principles of sound physics are not just theoretical abstractions, but the very fabric of our auditory experience. As we continue to unravel the mysteries of sound, we stand in awe of the intricate dance of vibrations and waves that fill our world. Stay curious, keep exploring, and who knows? You might just compose the next symphony of knowledge in the realm of acoustics. Thank you for watching. If you're hungry for more knowledge, hit that like button and don't forget to subscribe. Your support is incredibly valuable to us.